topics of this class already. So let's see. This week, we're going to wrap up this models for digital design. You'll learn how to analyze all these caps in transistors. And there will be a little homework here, and we'll do not next week. I would say probably Monday, the week after, the 15th. And so Monday and Wednesday next week, I'm going to cover, the circuit design for the SAR ADC. So which is part of the work. You can see the poster on the, in Burn Hall. Do you see that one? So it's going to be very similar to that one. So that's the course project of this class. So let's take a look at the weight of that project and overall grade. That 20% or so? About 10%. 10%. Still a lot, right? Okay. So none of the components in the SAR ADC design of the course project will be an ideal block, or some of the ideal boxes you have used in the first level of this class. So this design will be fabricatable. I mean, all these are transistors. So we have done that. So I'm going to give you the examples of it, and we'll add a little bit details like regarding how to calculate DNLs and NALs. And it can be an 8-bit. I think we probably want to do an 8-bit version instead of like 4-bit. And I'm still thinking about like if we should do a layout or not. Probably not. I mean, maybe just LT Spice simulation. Or we can build everything in electric VLSI and then simulate with LT Spice. Okay. Since I'm afraid that we don't have enough time to do the layout. It's a lot of work. And let's take a look at what we did last semester for the course project. Scroll down to the bottom, here's a web page for the course project. And that was just a simulation. Okay. Started there. It's just as a SAR block, no sample and hold, no op-amp, no DAC. 4-bit. Okay, that's how it works. You have to run this simulation, have to show these curves, which means it works, right? So how these digits are being plugged in sequentially. And eventually, here, okay? Basically, it's just repeating the work on the poster. Is that boring? You want to do a layout? You're like, no. You want to take a break during the Thanksgiving? You're ready for turkeys? Or visiting family somewhere, or just stay in Durango usually? Visit? For most of you, probably. No, you're not. You're not going to Vegas. I am going to Vegas. Not gambling. I don't like that since I don't have that much money to do that, to lose. I lived there for 5 years. I never gambled at all. So I don't know the rules. It can be very interesting. I think if I have money to gamble, I'm going to invest into the stock market. It's different, I think. Similar, very similar. I have seen people in Vegas, they're professional gamblers. They will lose, but after they're very smart, not just a random person, gamblers. They calculate it first, and so they know if they gamble for a certain number of times, then they get a 70–80% to win. So that's why they have actually very stable monthly salary by doing that. It's usually like $40,000 as a monthly income by doing that. It's very stable. It's not changing that much. Professional ones. Okay. I just go there for food. I just saw a deal online. A lot of the really top hotels on the strip are having a lot of discounts, probably because of the pandemic or something. All right. Okay, you can refer to that link. This is from the spring semester. Okay, so you can see the design of the star block. So what you need to add to it, first, you want to make it into 8-bit instead of 4 bits. And also you want to add a sample and hold circuit into it, and also op-amp circuit. So definitely the circuits are not going to be provided, but the report written by a student worked with me in the past summer, can be given to you guys. I don't mind, because they're just the figures. So can guarantee that you guys will get something out from it instead of like nothing. And I know you guys have procrastination, so start working on that as soon as possible. So I'm going to cover the details about it the first 2 days, first 2 lectures next week, and then cover the memory circuits. If we don't have enough, if we didn't finish all the memory circuits, I'm going to do it again after the break. Otherwise, I'm going to do power analysis and introduction to the IC industry. So this is for part of the, because I see that you guys have one question on the teaching evaluation form, right? So did I foster a positive environment to let you guys learn more about this topic, right? So I think it's good, because this is the first digital class you have learned in your life, digital IC design course. And there are many other ones you can take in the future. So this will bring you to the door, into that field, to encourage you to learn more about it, because this is useful, and can get you a job easily if you take some projects on this topic. And I just didn't fill in this space over here, since I don't know whatever will be left. Otherwise, if everything's done, all the important topics are covered, I won't just keep giving lectures during the last week of the semester. I would just give the time to you guys to work on the course project. There will be a lot of work in that, so hopefully you can get that credit. Okay. You want some refund from notation, since I didn't give lectures in the last week? Write a letter to the provost and report me or something like that. All right, so final exam, 2 hours, the same location, same time. No, 2 hours actually, 2 hours from 7:30 to 9:30. Okay, so that's the plan for the rest of the semester. So you can, use this plan to plan for your, flights or travel during the break, winter break, Christmas, right? Okay. All right, so let's wrap up the models for digital design. So remember last time we mentioned that if one side is charging up the cap on one side and the other side is discharging it at the same time, and the effective capacitance of this C is not C anymore. So physically it's C, but effectively here, C effective becomes 2C. Why? Because QCV, remember? Q equals to CV, like that. And this is here's a rising edge from 0 to VDD, and this is a falling edge from VDD to 0. Okay, so when this is charging up this cap, this is pulling the charges away from this cap as well at the same time. So delta Q, the Q change on this cap or in this cap is actually VDD times C effective and this equals to 2Q. And however, we know that Q equals to C times VDD. Or just write it down here, equals to Q. So in that case, we can find out actually C effective is what? 2C. That's how we get it. Right, because VDD times this C becomes 2Q, and VDD times C is only Q, so that's why CEF equals to 2C. Right? And when we model this cap, we can treat it as a circuit like this. Two C here, two C here as well. When we are just looking at here, it's going to be 2C. When we're looking at here, is 2C as well. So for every individual source, this guy is 2C to charge and discharge instead of C. Okay? But when you are looking at the overall cap here, it's not adding them up together. It's still 2C. But this is like just for each voltage source. It's 2C here. So the reason we have to model the cap in that way is because there are parasitic capacitance in MOSFETs. And so this effect, it's called the Miller effect. And now let's take a look at the MOSFET, how that works, how this works in the MOSFETs. First, if you only have C, there won't be any time delay. So there has to be some resistance. So when you model the channel resistance, have to consider the current and voltage being applied to the transistor. So for example, here is the NMOS. Oh, my brain's not working this morning. And we know that for NMOS, VDS, here's ID, and the curve looks like this. So here's VDD. And if we want to model the resistance, this curve is not linear. So you cannot directly use VDD over ID. But you can, when you are modeling that, you can assume that here's a curve like that, and the 1 over slope will be the channel resistance, not accurately, but approximately. It's 1 over the slope. Why? Because the slope here, the delta Y here is ID, the delta X is V, is the voltage. So it has to be 1 over the slope. So what's the slope? I have to look at this part. Here's VDD, here's IDS. So the slope will be IDS or ID over VDD, right? So what is ID? I forgot if I covered it in logic, but you guys should know that for NMOS, the calculation, so the way to calculate IDS is this square law equation. That's ID. So we're not going to use this to calculate currents in this class. This is microelectronics 2 usually. You have to calculate the current and to find the VGS for DC analysis, and then GM for AC analysis. But now let's assume this is ID over VDD. So 1 over slope becomes VDD over, so this is a constant. Okay. Which is what? Rn, the channel resistance of the NMOS. So for this circuit, originally VO equals to VDD. When I turn it on, what's going to happen for this transistor? Originally, it stores a charge of VDD over there, a voltage. When it's 0 for the gate, the transistor is off, right? So nothing is going to be discharged. But whenever I turn it on, it's going to discharge this cap to the ground, and until it becomes 0 volts over here, right? So for this simple circuit, you can model it. How do you model it? Just draw this. Because the transistor doesn't make too much sense for, it doesn't have any components or linear components in there. So when we are modeling that, we want to make it more intuitive. So we draw it in this way. So you can apply all these voltage and current laws for calculation. So that's the NMOS transistor. This is Rn. This is the drain. This is the gate. And this is the source. Why it has to be disconnected? So here's the channel, right? Whenever it's turned on, it's going to flow to the ground. Makes sense. What about here, the gate? Yeah, that's the switch. That's the dielectric material, right? Dielectric. That's why it's disconnected. Cannot electrically short it to anywhere because it's not making sense. That's why most MOSFETs are, consuming lower power because it's not continuously flowing current into it. This is manipulating the electric field to turn it on and off. Okay, so keep in mind, this is how you model NMOS over here for the digital model. And let's look at another example here with a NMOS with a resistor on the top. That's a gate, and that's a dielectric material. So there's a capacitance, parasitic capacitance over here. It's a cap. And when we model it, we divide it into two halves. And we consider here as 1/2 Cox, here as 1/2 Cox, because the overall capacitance over here is Cox. So what is Cox? It's Cox prime times A. So what is Cox prime? Epsilon R times, is from Wednesday's lecture. Epsilon R times epsilon O over Cox times A. So this is a constant. Cox prime is a constant. A is a variable. And we are designing the width and length of the channel. So A equals to W times L. Remember? So Cox is a capacitance of the oxide layer here. But when we do the analysis, we have to divide it into halves because both of the terminals have connections. So for example, this one has a connection here, has a connection here. So whenever this is being driven, sorry, it's NMOS, you drive it to VD from 0 to VD. So both of the capacitors are involved or engaged, one here, one here. And this is called CGD, the gate to drain capacitance. The CGS. CGD equals to, physically, 1/2 Cox. CGS equals to 1/2 Cox. I didn't short a cap over here. They are parasitic caps. I just modeled them like that. They are critical, because they exist and it's going to affect the time delay of the circuits. However, if this one is driving, it used to be voltage high and there's a load at the very beginning and stores VDD over there, which makes sense because whenever this is off, this is disconnected from the circuit. So the VDD here is going to charge this cap up to bring it up to VDD, right? It's same for if you have this connected to here, but you just connect the 0 volts to the gate. It's the same effect. This one will be charged up to VDD. Whenever this goes up from 0 to VDD, this one goes down from VDD to 0. Is that correct? Why? Because the MOSFET is turned on and it's going to discharge this one to the ground. The charges goes to the ground. That would question like, hey, it's still being shorted, not shorted, but still connected to the VDD through the resistor. So why this point when the transistor channel is on, it's going to be discharged instead of being pulled up to VDD? Resistance, right? Which one is easier? Going down is easier. That's why it's being shorted to the VDD to the ground, not VDD. Okay. What's the name of this resistor? Is that the low? Is that RL or R pull up? So remember we have a little RC on the top of the. I mean, this is not the question, but anyway, so this is the pull up resistor. Okay, can be used as a load, but now it's a pull up resistor, I think. And so this is after turning on, this cap will be discharged. So it looks like the same behavior as this cap. Just doing the same thing here, literally. So that's why we model it in this way, so we can understand it ahead of time. And now let's look at this one. Which one has a mirror effect? Which cap has a mirror effect? CGD or CGS? So look at CGS. Physically, it is a half cox. It makes sense. It's just half of the plate. And whenever I drive this up, is this one being dragged down to the ground or is already ground forever? It's already ground. So it's not pulling the charges away at the same time. It's already there. Not only one source is applied to it. They are asking, hey, this one is discharged to here. So is this discharge it's gonna contribute charges to this point? I mean, is that going to fluctuate that voltage at that point? Because you can see like charges are flowing through it. It's grounded. Permanent zero, very strong. Just trust the ground. Ground is a ground. It's going to be super strong ground. 0 volts forever. So still, it's going to be a steady 0 volts over here. No mirror effect. What about this one? Charging up, discharging at the same time. So it's pulling this down to the ground at the same time. So this guy has a mirror effect. So effectively, what's the capacitance over here in terms of when you are looking at the input? So, or you can say, now I got two caps in parallel, right? Physically a half cox and a half cox. So overall, physically, they are cox, one cox. But effectively, it's not one cox in terms of input. So it actually has a bigger capacitive load compared to the physical load. And what is that load to this applied to this point? have to consider that because you are driving down and down this point. You have to consider the capacitive load of it. Equals to CGS plus what? It's the effective input capacitance. Same for the output. So when you are looking at the output pin here, if you model the capacitance over here, right, you split that one. So now it's not one anymore. You split that half cox into, two coxes. So the other one as the output, because this is shorted to this pin, so actually the output has a cox as well. One cox, not a half cox. All right, because of the mirror effect. So the overall capacitive load as the output pin becomes cox plus C load. So C load is anything from the load. I mean, whatever is a black box has a capacitive load of CL. So CL plus C cox because they're in parallel, right? And usually, because the transistor is tiny, and usually the load capacitance is huge. So as the output pin, you can ignore cox as long as your load is large enough. You have 1 nanofarad plus 1 femtofarad. It's not making too much difference. So you can ignore this cox over here. But whenever you are looking at the output, you want to add a cox to it. When you are looking at the input, you also want to add a cox to it, and 1 cox plus a half cox, which is overall 2/3 of cox. Okay, clear? So if you model this thing in a resistor and capacitor circuit, it looks like this. Definitely if there's a load, right? C in N, so C in of the NMOS, that's cox N. So what is C in? C in N? What is cox N? Just cox N. Yeah, Cox, cox N. And CL depends on the circuit, what is given over there. And Rn is usually given. Okay, propagation delays. %, 90% of the amplitude, 90%, 10% of the overall amplitude. Same here, 1090, 1090, and 50%, 50%, 50%, 50%. And here are the definitions. From here to here, it's called TR, T rise. From here to here, it's called T fall. From here to here, so that's input, that's output. Okay, keep in mind it's different. So this is TLH, low to high, and this is high to low. And 50% to 50% from the input to output, it's called propagation delay. And measures at the 50% of the full amplitude of the input and output. It's called TPLH. So LH has to be the output. If the output is falling, then it's going to be HL. Okay, the HL or LH is determined by the output. So 50%, 50% is the TPLH. And here, 50%, 50% is TPHL. Also look at the output. These are the definitions. TPLH, TPHL, these are 0.7 RC because they were calculated from the 50%. That's where the 0.7 comes from. And we're not going to derive it. This is from circuit one if they derive it for you. But you can refer to my circuit one lectures, see how we derived it. It's not necessary to do it here. 0.7 RC is the propagation delay, and TLH, THL, these are different. They are not propagation delays. So these are calculated from the 90 and 10% of the amplitude, okay? And these equals to 2.2 RC. And you can refer to the textbook. It's on page 50 of the CMOS book to find out more explanations on these two. But now we're just directly using 0.7 and 2.2 RC to calculate these delays. Okay, whenever it's TPLH, TPHL is 0.7 RC. Whenever it's TLH, THL is 2.2 RC. So let's look at one example here. I'm so hungry. Did you bring a lunch with you guys? Example. Estimate the rise, fall, and delay times definitely the output signal. We are talking about the output signal. Of the following circuit. This is on page 320 of the textbook. So 10 to 1 here means exactly 10 micron over 1 micron, right? Just keep in mind. And here's a table for the parameters. So all these parameters can be found on the textbook. This is a 1 micrometer technology of on the textbook. This is on page 317. Estimate the rise, fall, delay. As the output point, right? So when we're talking about output point, you don't have to look at the input. Just look at this part. So I can pull this out. Okay, so the way you model it is, because this one shorted to here, so it's going to have a cox here. It's a mirror effect cox. Oh, sorry, cox. C lobe. So the rise and fall time as the output are actually the LH, TLH, and THL. And the delay times are the TPLH and TPHL. So as we have calculated TLH equals to THL, which is 2.2 RC, which is 2.2 times R and C. R is Rn, C is C total. So C total equals to 2 times Rn will be 1.5 K. So C total is this plus this. And for this 10 micron over 1 micron, which is exactly the same size as here, so C total equals to cox plus the load, 17.5 plus 50 femto. And then do the calculation, somewhere around 220 picoseconds. And also TP, because whenever the switch is closed for this circuit, what's going to happen is it's discharging this cap. So the voltage here is actually HL. So for the propagation delay is TPHL, which is a 50-50%, right? It's a 50-50% analysis instead of the 10% and 90%. So it's this one. So TPHL. So TPHL equals to 0.7, which is 0.7 times Rn times C total. So this calculation is pretty easy actually, 0.7 times 1.5K times C total, which is 17.5 femto plus 50 femto. And eventually you're getting somewhere around 70 picoseconds. It's very trivial. And now let's look at the model for the PMOS. That's C lobe. So Cox P, which one has a, so this is CSG, right? CSG, C, GD. Which one has a mirror effect? This one. So this is effectively Cox instead of a half of Cox, right? So here's a model for the PMOS. C load, Cox P as the output. So we are not drawing the input, right? So this is output pin here. This is RP. And if you have to draw the input, yes, so it looks like this. And so this becomes C ox, sorry, 2/3 of Cox P. But when we are just looking at the output, then that's the model of the PMOS. All right. If this one is also 10 over 1 micron over 1 micron, so what is TLH? You can calculate here. What is TLH? Use the same parameters. So these are the parameters here, right? So RP and Cox P is based on 30 micron over 1 micron. And now this is 10 to 1. So how can I convert it into 10 to 1? So what is RP here? Which one is wider? The one in the table is wider. And it's 1.5K. So for 10 micron over 1 micron, it becomes what? Higher resistance or lower resistance compared to 1.5K? Same length. So actually should be, so 30 micron over 1 micron is 1.5K. So what about 10 micron over 1 micron? So the resistance will be higher or lower? So the same length, right? So this is a piece of resistor. 10 by 10 is this. It's not changing the length, okay? So 10 by 10, 30 by 10. Which one has a lower resistance? So the current flow in that way, not this way. This way. So here's a piece of resistor. And the same, it's a 3 times wider piece of resistor and current flow in that way. Which one has a lower resistance? Which one has a lower resistance? This one, right? Why? Because R equals to what? Rho LA. So what is changing over here? There's two pieces, two resistor rods. What is changing? Area. So area is getting bigger, so resistance is smaller. L is not changing. This is L, right? It's not changing. It's wider, so that's why the cross-sectional area is bigger. So you have to change the resistance to 4.5K. So what about cogs P here? 3 times smaller. So the area will be 3 times smaller or 9 times smaller. So what's the area here? 30 times 1, 30. What's the area here? 10 times 1, 10. So the area for this new PMOS will be 3 times smaller. So what about the cogs? So C equals to epsilon A over D. So A is 3 times larger, so got 3 times larger C as well, right? Which one is larger? This is larger, right? And this is smaller, this is 10 to 1. So the cap here is 52.5 femtofarads. So the cap here should be whatever here divided by 3. And that's exactly 17.5 by chance, right? It's not intentionally to match with this capacitance, it's NMOS. But this divided by 3 will be exactly 17.5 femtofarads. So since you know this, it's pretty easy to calculate, just use the equations. So TLH is 2.2 RC, which is 2.2 RP cogs P 4.5K times, have to add these two together, right? Cogs P plus CL, 17.5 femto plus, what's the CL? CL is also a 50 femto here. Which is 660 picoseconds. TPLH. Whenever this is turned on, it actually flows. It charges out the cap from VDD. So originally that was 0 here. So that's why it's going to be TPLH, right? It's low to high, equals to 0.7 times 4.5K times 17.5 femto plus 50 femto equals to 210 picoseconds. Almost done. Almost there. The last thing I'm going to cover is a model for the inverters. We have analyzed the individual NMOS and PMOS. So what's the digital model for this guy? It has a cap here, has a cap here, has a cap here, has a cap here. My goodness. So from the input, get person here looking into the input. What's the cap? What's the C in? What is C in of the inverter? Equals to C in N plus C in P, right? So what is C in? Then C in N here for the NMOS, C in the input capacitance for the NMOS is 2/3 of cogs N. We have done that just now. And C in P, 2/3 of cogs P. So C in overall will be 2/3 of cogs N plus cogs P. Okay, that's the overall input capacitance. So how do we model it? Input 2 gates, no electrical connections, but there are caps. One goes up, one goes down. So the one goes down is C in N, which is 2/3 of cox N. The one goes up is C in P, which is 2/3 of cox P. And nothing in between. And then here are the channels. RP, RN. And 2 more caps. What are they? So this is one model. It's a one circuit model for one inverter. How to draw it? So what are these caps? Remember, this cap or this cap. So these 2 caps have what? What effect? Mirror effect. And these were shorted to the output, so that's why the output is going to have a cox P here and cox N here. That's how we model it, okay? Whenever the inverter is pulling this pin up, the caps are in effect because these 2 caps are being shorted to here, but Rn is not in effect because Rn is at the bottom, it's not flowing any current to it. When this one being put up to VDD, so here is involved and the 2 caps are involved. Otherwise, only Rn is involved and also the 2 caps are involved. RP is not. Keep in mind, when we're calculating for TPLH or TPHL, it's going to be different because R's are different. Only when R's are equal, you can use the same resistance, but otherwise, you have to be careful about it. So really quick here, TPLH equals to what? 0.7 times. LH is driving this output pin from low to high. So which resistor is working there, is functioning? RP. What's the overall capacitance being added? What's the capacitance load being added to this pin? Both of them. So the capacitances are the same, but the resistance is not the same. All right, keep in mind. Pretty much done. And one more topic next Monday. All right, we'll see you next week.